So, you're prepping for a physics exam, and you know those energy problems can be a total headache. But what if I told you that you could solve almost any of them just by thinking like an accountant? Well, that's exactly the roadmap we're going to build right now. Let's get into it.
This is the big question, right? You learn about forces in one chapter, rotation in another, and energy somewhere else entirely. But the really tough exam questions, they make you connect all of them. That's the connection, the big aha moment we're aiming for today.
All right, so first stop on our map. We need to understand the fundamental rules of the game. And that means talking about forces and work. You see, in physics, every single energy transaction is governed by the forces involved. So let's dive in.
Think about it like this. A force is basically what causes energy to move around or change its form. The good news is, when it comes to balancing the energy books, there are really only two types of forces you need to keep track of.
Okay, let's take a look at our first type of force. You see these two paths, both going from point I to point F? For a force like gravity, the amount of work done, which is just the energy exchanged, is exactly the same for both paths. It doesn't matter if you take the long, scenic route. All that counts is where you start and where you end.
And that idea that the path doesn't matter, that is the absolute key to what we call a conservative force. And there's a good reason for the name conservative. It's because the energy isn't lost. It's conserved right there in the system, ready to be used again. It's kind of like putting money right back into your bank account.
So this really breaks it down for us, right? It's the two sides of our energy ledger. On one side, you've got your conservative forces, like gravity. They act like a savings account. The work they do gets stored as potential energy, and you can get it all back. But on the other side, you have non-conservative forces like friction. Think of these as transaction fees. The work they do absolutely depends on the path, and that energy is gone. It leaves the system as heat. It's not recoverable.
All right, so we've got the rules of the transaction down. Now, what about the actual currency? What are we trading? This brings us to the second scene in our roadmap, the currencies of motion.
You know, we all learned that kinetic energy is the energy of motion. Simple enough. But for your exam, you got to track two different kinds of motion. There's an object moving in a straight line, we call that translational, and there's an object spinning in place, and that's rotational. Each one has its very own kinetic energy account that you need to watch. And this table, honestly, this is one of the most powerful analogies you can get in your head for mechanics. For every single concept in linear motion, there's a direct equivalent in rotational motion. Mass becomes moment of inertia. Velocity becomes angular velocity. Even the formulas for kinetic energy look almost identical. If you get one, you get the other.
Okay, but what is this moment of inertia thing, really? Just think of it as rotational mass. It's a way to measure how much an object resists being spun. But, and this is the key, it's not just about how heavy the object is. It's all about how that weight is distributed. You know, like when a figure skater pulls their arms in to spin faster, they're actually changing their moment of inertia right there on the ice.
And this is why shape becomes so important in these problems. A hollow hoop and a solid disk, even if they have the same exact mass, will have totally different moments of inertia. Why? Because their mass is in different places. The hoop has all its mass far from the center, which makes it harder to get spinning. You're going to want to have these common shapes in your back pocket for the exam. So this all brings us back to the money, right? The energy currency. The bottom line here is that rotational kinetic energy is a huge account that you have to track. The faster something spins, or the harder it is to get it spinning, the more energy is stored up in that rotation.
Okay, buckle up. This is it. The final scene, and honestly, the most important part of the entire map. We've got our rules, we've got our currencies. Now it's time to put it all together with one single powerful idea and finally balance the books.
So, let's start simple. Let's start in that perfect physics land you see in the early homework problems. You know, no friction, no air resistance, none of that messy stuff. In a system like that, where only conservative forces are doing work, the total mechanical energy, that's just kinetic plus potential, it stays perfectly constant. And that simple idea gives us this absolute cornerstone of an equation. It just means that the total energy you start with is exactly what you end up with. Sure, it might change form, like potential energy turning into kinetic energy as a ball falls, but the total amount of money in the bank never changes.
Yeah, but we all know the real world, and more importantly, your exam, it's never that clean, is it? So this is the million-dollar question. How do we account for those energy leaks from things like friction? What happens to our nice, neat equation then?
Well, the answer is this. Seriously,
This little equation right here is the master key to pretty much everything. If you're going to tattoo one thing on your arm for the exam, make it this. The work done by non-conservative forces always equals the change in the system's total mechanical energy.
So let's break that down piece by piece. The term on the left, WNC, that's the energy that got taken out of your system by friction. Those are your transaction fees. The term on the right, delta EM, that's just the net change in your energy accounts, your final energy minus your initial energy. These two sides always have to be equal. Look, no matter how crazy the problem seems, with ramps and pulleys and spinning things, your job as the energy accountant is always the same. Figure out your start and end points. Account for any fees you had to pay to friction along the way. The final balance has to make sense. Every single joule has to be accounted for.
And here's the final piece of the puzzle. That lost energy, where does it actually go? Well, remember the first law of thermodynamics? Energy can't just vanish. That work done by friction, that W sub NC term, it has to go somewhere. And where it goes is into thermal energy. It becomes heat. And that right there, that is the exact spot where mechanics plugs directly into thermodynamics.
So let's just end with this thought. We learn physics using these perfect, ideal systems, but the real world is messy and non-conservative. Understanding and accounting for these energy leaks and transformations, that's really what engineering is all about, whether you're building an engine or tracking a planet. And now, you've got the roadmap to account for every last joule.